Okay, there we go. How Affirm leverages AWS services to support a unified data lake. So first of all, I'd like to give you guys a little bit of context about Affirm and what it is that we do. Our mission is to deliver honest financial products that improve lives. And basically the way that looks is if you think about credit and consumer credit in particular, it's just this really important tool. But when you look around and you look at how customers feel about their financial institutions, they don't have a lot of confidence that customers have the best interest, or that the financial institutions have the best interest of the customers in mind. So the idea was, can we create a company that puts the interest of their consumers first, that really tries to do right by their consumer? And one example of that is, for example, we never charge late fees because we don't want the revenue source for our business to be correlated with something that is not good for consumers. I think this quote by Max summarized it best, which is, Affirm is reinventing consumer credit. We've created a simple way to offer honest consumer financing that is fully aligned with the best interests of our customers. And the way that we do that is we offer loans online at the point of sale. So it's a product that we've had from the very beginning, and it's been very popular and very successful. And we'll integrate with merchants. We have thousands of merchant partners. We'll integrate with them at the point of checkout so that when you want to go and use credit when you're checking out, instead of using a credit card, you can select Buy with Affirm. You'll give us some information about yourself, and we'll run a machine learning model that makes a real-time underwriting decision and give you your loan. So that's great. We also have in-store, where we partner with merchants to allow the exact same process, but in-store when you're at the checkout counter, take out a loan with Affirm. And then finally, if you're working with a merchant that doesn't support Affirm, you can always go on our app, tell us how much the purchase costs. We'll go through the same process, and we will give you a one-time use credit card that you can put in on the credit card rails. So that's what we do. To kind of give you an idea of the scale of our business, we currently have millions of customers, millions of loans, thousands of merchants that we work with, multiple credit warehouses and loan buyers who help us fund our loans, over 700 employees and growing, and we're in 4 offices across 4 cities. So obviously for us, as with a business of any scale, data is going to be really important for us to continue to grow and to improve and deliver great products. So just wrapping this up so you have an idea of what it is our product does. When you go to a merchant, you check out with Affirm, you'll give us some information about yourself, and then we will give you your terms, very clearly tell you how much your credit costs. You're going to accept it, at which point we pay the merchant sends the customer the item, and we service the loan, and the customer can pay back on the terms they agreed on, 3-month, 6-month, 12-month. So we're going to be talking about data, and in specific, we're going to be talking about a data lake. It's this concept that I think we've heard a lot here at reInvent, and it's worth thinking about what exactly is a data lake and what do we want from it. So here are some definitions. AWS says that a data lake is a centralized repository that allows you to store all your structured and unstructured data at any scale. You can store your data as is and then run different types of analytics. Wikipedia has a similar concept, which is a data lake is usually a single store of all enterprise data, including raw copies of system source data and transform data used for tasks such as reporting, visualization, advanced analytics, and machine learning. So I think there's a few key points here to parse out in our understanding of what it is we're trying to build and why it's valuable. And I think the first thing is this concept of a centralized repository or a single store of all enterprise data, right? We want a single place where we're putting all of our data so it's accessible in the same way and we can join it together and extract analytics out of it. And the second idea is structured and unstructured data, right? And I think this is what makes the data lake kind of a larger concept than the concept of a data warehouse. In that when you're working with a data warehouse, you've got schematized data, it's highly structured, and you're able to work with that. But what about our unstructured data? What about our data that we don't necessarily know how to structure yet? Are we just going to throw it out? Well, we don't want to. We can actually extract insight and use that data as well. So we need a place where we can put that and still be confident that we can get value out of it later. So that's what we think about when we think about a data lake. So that's a data lake. What do I mean when I say a unified data lake? Well, it's really not going to be enough if I go and put a whole bunch of files in S3 and then tell my business or my organization, we have a data lake, we're good, don't have to worry about anything. We're not going to know how to get at that data and how to actually use it. So we need to build a layer of organization, a layer of richness on top of this repository for all of our business data. And what that really means is, first of all, as we talked on the previous slide, centralized, right? You don't want to have to think about, oh, well, this data is over here and this data is in this completely different system over there. So it's going to take me some time to figure out how to bring those two sources together and where do I put it? That's a problem. And on top of that, you want it to be standardized. And when I talk about standardization, I really talk about structure, right? You want to structure your paths, you want to structure your formats so that you understand where your data lives and how to understand it. And once you have those two things, you want to make it discoverable, right? You want to have some sort of tooling where you can actually go and look at what data do I have, what is it, what does it mean, how do I use it? When you have those three things, all of a sudden you've got usability, right? And then you're going to think about, well, how are the users who need this data going to get at it? How are we going to use this data as a business to provide value for all of our use cases? And then there's this other point, which is you want it to be a definitive source of truth. And I mentioned this, it may seem obvious, but I mentioned this specifically because as you'll see how we do the data lake, all the data is not always going to be queried directly out of your data lake. You may want to load it into use case specific tools, systems that are optimized for various use cases that you're trying to solve for. But you really want this data lake to be that source of truth. So one, you can replay out of the data lake if there's any discrepancy in your replication. And two, you can always go back to the data lake if there's a use case where you find that that is more valuable. You don't want kind of disparate systems where some data's here, some data's there. It comes back to this concept of everything being unified. So we know what a data lake is. We know that we need some organization, some structure to be able to do what we want to use our data well. What does that mean in terms of AWS? Well, when we talk about this central repository of data, structured and unstructured, inside of AWS, that's going to be S3, right? S3 is this highly durable, almost infinitely scalable store of data. And so when I say data lake, I'm saying I'm putting stuff into my data lake. I'm really talking about putting things into S3. And then we've got all these other AWS services. And when I talk about using Lambda, using Kinesis, using Glue for discoverability, I'm talking about data lake tools. These are the tools that are going to bring that layer of organization and that usability to our lake. So you end up with something that looks kind of like this at a high level, which is this data lake as this central component where all of your data is going into, and it's fueling your analytics, your reporting, and your machine learning. And obviously, you're going to have many more sources than this, but this is a summary of how you can think about this. And at Affirm, we're using our data for countless use cases. I wanted to highlight a few just to give some context. Business analytics, I think this is the first thing you would think about when you think about data system, is fueling BI, business intelligence, to be able to understand how your business is doing, where you're performing well, where you're improving, where you need to improve. At Affirm, it's also very important to us for machine learning, right? Our underwriting model is a machine learning model. We need to be able to pull data from any source that seems interesting, to experiment with our model, to iterate on it, and then to actually train it and build it successfully so that it can make good underwriting decisions for us. And also, because we work with financial institutions to help fund our loans, we're doing a lot of warehouse loan buy reporting and loan sales selection. So these are processes, reports that are really specific to our business that really pull a lot of data we know about the decisions we made about a customer and their loans together in interesting ways. There's also third-party integrations. This is basically, you're going to be using third-party tools to provide additional insights for you. And you want to bring that back into your data lake because that data is also connected to things you have in your internal systems. So you want to bring that back in. And the last one, which I don't hear talked about very much, but I think is actually very valuable, is for debugging monitoring. Obviously, you've got your real-time monitoring systems. You need those in order to stay highly available, respond to issues quickly. But you also can put these logs and this monitoring into your data warehouse, and that makes things like log diving and evaluating long-term trends, maybe your rate of failures over the year in your CI system. It just makes that so much better, so much easier. You can connect that with other data and make correlations on your insights. So for the rest of this talk, I'm going to talk about how we actually do all these things, how we're using AWS tools to ingest all of our data into our data lake, what we're doing with that data lake, and how that's helping fuel analytics, reporting, and machine learning. And I hope that you guys take two things away from this talk. The first is if you're thinking about how to improve data at your organization or building a data lake or what you want to do with it, maybe some of the things that we've done will be interesting to you and help you in your decision making. And the second thing is I really want you to start thinking about this concept of a data lake as a central piece of everything you do with your data. So even when you look at this diagram that I have over here, we're using it for analytics, reporting, and machine learning, But we're actually going to take what we extract, those insights that we extract from our analytics, our reporting, and our machine learning, and we're going to put that back into our data lake. We're going to expose that as new sources. And so you're kind of iteratively building this, this richness of data that you can use for all sorts of use cases. You've got a new use case or a new product coming out, you can pull from what you've already done. It's really important. So with that, I'm kind of going to dive into our implementations of some of these things. I'll start with logging. So we've got, our application logs as well as Nginx logs, system logs, other type of logs that are going on our nodes. We're going to stream that obviously into a real-time system so that we can do real-time debugging and have visibility into our observability stack. But we're also going to rotate that on a certain interval into S3, and that's where it's going to enter our data lake. So a few things that we do with our logs that helps us out a little bit. First of all, we're going to have a standardized logging format. So we have a logger. We'll vend a logger for any language that we support. So every service that we have is going to log in the same way. And we're using JSON formatted because it's readable by humans, but it's also really easy for CRD with applications. And every single log across any service that anyone builds is going to conform to this format. Now, obviously, this isn't the only format we have, right? You've got CloudTrail logs, you've got your Nginx logs. There's logs that you really can't control the format of. So you're already going to be dealing with a lot of formats in your data lake. There's tools that are going to help you with that. But we're not going to make our jobs any harder by also having to deal with different formats for different services. We're going to standardize that. And in the data lake, a single parser can process them all. And in our case, we're capturing some important characteristics here, IP, function call, region or AZ. And then we've also got a custom JSON map of additional attributes so that, who knows what someone wants to log, they can still pull that out in a standardized way later. And likewise, your paths are important, probably pretty obvious. You got to put it somewhere. But in our case, what we do is every service is going to conform to the standardized path format. So even if you have a standard in one service, if there's a different standard in another service, it's still going to be a little bit weird. And the nice thing about this that helps a lot is right off the bat, without doing anything else on top of this, if you're in Spark or a Hadoop-based tool, you can already start filtering based on path. But that's not really enough. Not everyone's using Spark. There's a whole bunch of other use cases going on here. So we're going to use Athena and Redshift Spectrum to make this discoverable. And what we're going to do is we have the simply tail that we run in EMR that is going to convert this into Parquet. And we just convert it into Parquet because it's a columnar format. It's going to make performance faster when people are creating this data lake for specific columns, which is often what you have. And then we're going to register that as a partition. We use hourly partitions into Athena and Glue. And what Athena and Glue are going to do for us is they're going to make this really discoverable. Athena has a native integration with Spectrum. So Spectrum means you can query this data in Redshift. And so now you can query this data in your data lake in these S3 files with SQL, right? And so now this is a lot more valuable for doing analytics. So here's some simple ones. You can do a count of all the logs from a certain day. You can zoom into a certain service where the error logs are, or even to a certain host in a certain time range if you're trying to do debugging. And these are obviously very simple queries as an example here, but you can get a lot more advanced here. This is in your SQL and it's connected to all your other data sources. So you can start connecting your errors to other logs you may have, CloudFront logs, other business logs to try and understand what's going on. So we'll move on to metrics. Our metrics architecture, specifically here, I'm going to be talking about application metrics because those are what we find more valuable in our data lake. Things like CPU, memory, it's totally fine to just have that in your real-time, metric system, whatever you're using. But application logs can actually have a lot of value when you're doing higher analytics processing because it tells you about what your application did. It's often connected to, your users or your flows, so it's really valuable. So real time, we're sending to a tool called Remint. It's an open source tool, which does metric aggregation and provides us a standard interface for how we send all our metrics, similar to a StatsD or something like that if you're familiar with it. And that goes to our real time monitoring stack. We're also going to log those metrics, and we're going to rotate those into Amazon S3. And we're actually using the exact same logging format here as I talked about in the previous slides, which really just means that metrics are no different than logs. There's no special case here. We can keep doing the exact same thing that I've already talked about. Here we're looking at a log for a certain host, and we're looking at a SQL store, like connection pool. And so we can do the exact same thing here. There's nothing different here. The only thing that changes is we're gonna register a new table, right? We're gonna register a table that is a view of just the metrics, just your metric events that you have. So for metrics, we're gonna do a little bit more on top of this to improve usability and query speeds. We have a lot of metrics, and we're gonna partition on fields that we know people are gonna frequently query on. So that service, you usually want to see, what are the metrics for my service? You might have specific metric IDs that correlate to other data in the system that you want to filter on as well. And then there's really specific use cases that we have where we know that certain offline processes are going to filter on a specific set of metrics and then analyze those further to generate more statistical or analytical modeling of those things. And we don't want them to have to do that filtering every time, so this essentially we're going to create a materialized view, right? We're going to filter on that, and we're going to expose that as a new table in Athena in order to make those queries faster for that use case. So now I'll talk about how we do click tracking. We have clients, and we'll send through an Elastic Load Balancer to an Nginx. And these click tracking events are everything, page load times, what the user interacted with in our app. They're schematized. Every single event type is schematized here. And Nginx is going to receive those requests. It's going to send it through a real-time pipeline. Again, you're seeing this pattern emerge where we want to see these things in real time, but we're also going to buffer them into a log and log rotate them into S3. And so, this might start to get pretty repetitive, but I think the point that I'm trying to make here is that you've got all these different data sources. When they're coming in, you can start to treat them the same way, and you can unify them all through Athena and the Glue catalog. And as you'll see even in my future slides, we really rely on Athena and AWS Glue to provide this discoverability layer on top of our data lake. So third-party data is a little bit different as far as how you ingest it in, but it's really a very similar concept at the end of the day. We use third-party data for Salesforce, tracking analytics, marketing analytics, customer service vendor data, and so on. And there's different ways to get at this data. And the core idea here is don't leave it in those systems. Write something that pulls them out and puts them into your data lake so that you can connect that with your other sources. We standardize the paths. Sometimes a vendor will have multiple tables within the path. Salesforce tables are a good example. So we'll have subpaths under the vendor. And then you can use the same Athena partition registration. In this case, we're using daily partitions because we just find that is how we're using this data is kind of on a daily aggregation. And so we register those partitions daily into Athena. Okay, so we've talked about these three cases of logging, metrics, tracking. Those all, we think about them as essentially a logging use case that we're registering into our data lake. Now we're going to talk about database replication. Our database and internal data stores are obviously a very rich view of what's going on in our app, and you're going to want to connect those in an offline analytics environment to do analytics, to do reporting, to do machine learning, to fuel the types of insights that you can gain here. So at Affirm, we have two databases that we use. For relational databases, we're using Amazon Aurora MySQL. It's an Aurora managed MySQL. That is a really great service. And for NoSQL key value stores, we're using DynamoDB, obviously a very scalable key value store on Amazon. And we have these requirements. We want to be able to get full dumps, so full views of the table in our data lake. And we also want to be able to play incremental changes into there. Dynamo tables, we obviously also need to consider. And right now, we don't yet have a near real-time requirement for this. So we can tolerate some replication delay, and we end up doing all these things in batch because of this property. So first, how are we taking snapshots? And the goal here is to provide very accurate nightly snapshots into our data lake, views of our databases, into a data lake format that we can use in offline analytics and for use cases where it makes more sense than actually hitting your online DBs. Lake Formation came out recently, and they have a way that may simplify this quite a bit. But at the time that we built this, what we actually relied on was Aurora's Select into S3 feature. It's called Select into Outfile S3. And what that does is, it's really a lot what it sounds like. you're going to give it a select statement, and it's going to dump the results of that select statement into an S3 path that you specify, S3 prefix that you specify as CSVs. So what you're seeing going on here is we have a bunch of database clusters. We've got a special read replica on each of these clusters that is for running these exports. And we're putting it into a pool just to avoid overwhelming the read replica with too many concurrent exports. And each of those tasks is going to run a select into out file S3, going to land those files. We're going to convert it into Parquet because this is highly schematized data, and we know it's going to be columnar as far as how it's being processed in this use case. So again, we're going to use Parquet as the central format, and we're going to register it into Athena and to the Glue catalog. A little bit more of a deep dive into how we do this. We have a pipeline that starts with the concept of a service, and a service is composed of multiple schemas, databases, and those may have tables in them, several tables or many. Each of those tables, we're going to split up the key space, the primary key space, into a series of chunks, where each chunk has a primary key range. And then for each one of those chunks, we're going to run a select, from table in the range into S3, and we're going to prefix that S3 path. We have the standard path, then we have the date, schema, table, and the prefix of the range that we're exporting. Why are we doing it this way? We've just found that splitting it up into pieces like this is a lot faster than doing one single select star from table into S3. So this is really a parallelization mechanism that we're using. And again, we're putting it in a pool because we've also found that if you just let this go unbounded, you start to impact your performance because you're overwhelming your read replica. So we're putting it into a pool, and these things execute. And once they're all complete and you land all of these part files into your prefix path, you're going to end up with a view of the table where, if you load this date, this schema, this user, into a Spark data frame, or you register it into Athena and you query it, you've got a full view of your table. Cool. So a lot of the consumers of this, we obviously will use this with SQL queries and for analysis purposes. But actually, a lot of the consumers of this, what they want to do with this is take these internal data stores that they also have online and run this complex business logic across the entire database, full scan the database, joining with other data sources to create reports, to create reports and so on. So we provide a library, since we know this is happening in code, that's just going to provide a really simple, easy interface for getting these data frames over these DB snapshots. And this is basically a layer that is going to provide a lot of utility for writing these jobs. It also allows us on the back end to change location formats, make file format changes, and abstract that away from the customer, the users of this API, just from, just by updating this library. Here's kind of an example of what this would look like. You just pull a data frame, you tell it about your schema, you tell it about the snapshot date you want, and then you can do something like, in this case, a simple join of two data models. But you can also go on, Spectrum or Athena and do this in a more exploratory way, or a way that you don't have to write a job for, or you don't have to write any code for. And what's beautiful about these two things, and the reason I bring it up as an example, is this is two very different ways of accessing this data. We're querying the exact same data sources, right? We're still querying all of this out of our data lake. So for continuous replication, we use a tool that AWS vends called AWS DMS. And AWS DMS, you basically give it a source, you give it a target, and it's going to replicate that data continuously. And what you can also do is tell it first load the data from the source, and then start continuous replication. Since we're using Aurora here, this is the MySQL bin log that does the continuous replication. And we're using DMS to load into two places. First, we're going to load it into Amazon Redshift. Amazon Redshift is our data warehouse. And for highly schematized data like our databases, Amazon Redshift is going to improve the performance of the queries that we run there. But we're also going to take that data, and we're going to only stream the changelog into S3. And the reason we're only streaming the changelog is, again, on the previous slide, we already have the nightly snapshots. So the changelog is something you can combine with your previous nightly snapshot to have this incremental view that's going to be faster than nightly. So DMS really solves a problem here, especially in terms of Redshift, of just doing the full load and the continuous replication without us really having to write anything at all there. DynamoDB replication. DynamoDB replication provides a similar thing to the bin log with DynamoDB streams, which is a continuous change log of everything that is happening on Dynamo. So what you can do is you can build a serverless system here where we plug in a Lambda that's going to pull, get invoked when new data comes in the DynamoDB streams. It's going to convert the DynamoDB serialization format into a more standard serialization format for our apps. And then it's going to write that into Kinesis Data Firehose. And Kinesis Data Firehose, you can configure it to send into S3 as a destination, and it'll buffer those events and dump them into S3 periodically. So again, this Lambda is just a pretty simple thing that's going to pull the data, decode it, handle it, and send it through into Firehose. And what are we actually using this for? Well, a few examples that we're using this for is to take the data in our data lake and, again, land it into Amazon Redshift and also into use case specific Postgres DBs that we use for a few different use cases. And what we need to do, the reason we need an ETL here in the middle of this is this for a certain period of time that we want to land basically upserts into these data targets. And what you get from the change log is, in a certain 15-minute period, you may have an insert and an update on the same hash key. So we actually want to write a pretty simple ETL that only picks that latest value, that updated value, and gives us that view of what are you upserting into there. And you may be looking at this, if you're familiar with Firehose at all, you may be saying Firehose can dump directly into Redshift. You don't need to build this. We really want to handle upserts here, which is what Firehose doesn't do for us. So what you can do instead is dump it all into a primary initial raw table and then do what this ETL is doing in Redshift. But that adds additional load on Redshift, and here we're kind of offloading that somewhere else and then loading it back in. So that's why we chose to do it this way. So a quick recap of databases. We're going to be using Aurora here, selected in Alpha OS 3, which is really going to help us avoid that intermediate step of having to copy everything locally and then copy it up to S3 ourselves. We're vending libraries for common data lake programmatic access patterns that are going to help you with discovery and usability. Obviously, this discoverability is also available through the Aurora and Glue registration that we do. But if you know people are accessing this data with Spark and you provide another layer there, it's just going to make it that much easier for people to implement things. We're doing continuous Aurora to Redshift and to S3 with a single tool, AWS DMS. And we have this serverless pipeline for Dynamo replication using DynamoDB streams, Lambda, and Kinesis Data Firehose into S3. So I've covered a variety of use cases of how we're getting data and ingesting it into the data lake and making it discoverable. And now I'm going to talk about how we're consuming that data and what we do with it. So for our analytics requirements, our analysts are expert at SQL, so we need a really good SQL interface for them to use. These queries need to return in a reasonable amount of time so they can iterate and do their analysis. And once you have your queries, we need to be able to visualize the data so that we can create reports, dashboards, and things like that. So we're using Amazon Redshift, which is a lab petabyte scale data warehouse with a Postgres interface. And it has this integration called Amazon Redshift Spectrum that I mentioned a few times, which allows you to query data directly out of the data lake without actually having to load that data into Redshift. We also do use Redshift directly because with Spectrum, you have to partition your data properly in order for your queries to be performant. So when you know that users are always going to query on a certain field or a small set of fields that you can really optimize for, you can create that partitioning and use Spectrum. But the problem is if sometimes users query on a field and sometimes they don't, and that field has a high cardinality, when you don't query on that field, you're going to scan a lot of small files, and Spectrum is actually going to become really slow. So we kind of balance these two things, and we try to figure out where do we have use cases where we can be very specific and utilize Spectrum and not have to put more data into our warehouse, pay for that storage space, so on, and when is it going to be better, more performant to put that into Redshift. So we have these ETLs where we're either going to do the additional analytics transforms on top of the data and load it into the Glue catalog and expose that via Spectrum, or we're going to ETL it directly in the cases that we need to. And you can join this data together now in your data warehouse, right? So you can join the data from your data lake and what's in your data warehouse. I really think about the data warehouse in Redshift as a component of our data lake. And another thing to mention about this copy is the files still land in our data lake. They still land in S3. The way you do the copy is you land it in S3, and then you load it into Redshift. So we still have this data there. You can still register it in the Glue catalog and utilize that as well. It's just a summary of what you do in Redshift to do these things. Pretty standard, well-documented things that we load the data in with. And we're doing all of these transformations in Spark. And I'll talk a little bit about more of that later, but we're using EMR very heavily for all of these. Spark is this framework that when you write your transforms and your queries, it's a very scalable architecture. You can scale it up. You can increase the size of your clusters. EMR allows us to do that without really having to think about cluster management at all. It's managed, and we use ephemeral EMR clusters. So when something goes wrong with one cluster, we can very casually shut it down, let new jobs spin up a new one. So we'll talk a lot more about that later, because I think it is an important component here. And then I'm not going to spend too much time on visualization because I think it's relatively well understood. There's many tools available. We use Looker and Superset, but you can use Tableau or some other tool that you can go to the expo and learn about. But basically, you need one of these. Our analysts are going to go in there. They're going to craft their SQL. They're going to create dashboards. These are consumed, by everyone from executives down to, regular employees. Totally great. So now we'll talk about reporting. And we have a lot of reporting use cases at Affirm. There's business metrics reporting, which is obviously what you would think about initially when you think about reporting. We want to make sure we can track our goals and progress. And we're going to use these visualization tools that can connect to our SQL query engine in order to do that. We've also got a lot of external merchant reporting, right? We work with a lot of merchants. And to them, we're a tool that increases their conversion rates. And so they want to know what is the auth capture volume for the merchant, what are the conversion rates, and we're still going to use our same tools to do that, but we're going to export them into a view that the merchants can consume. And then the third one that is really specific to us, I think, is credit warehouse and loan buyer funding reporting. And these are basically, we have financial partners that we're working with to fund our loans. And when we make deals with them, they have a lot of requirements about what they want us to tell them about the loans that they're funding. So this data comes from our internal bank engineering systems and our software ledger. These are system data stores. And they're generated from our data lake using our DB snapshots. So I want to take a closer look at this, because I think it's a really good example of where your data lake really becomes a powerful tool. In this case, not just for business reporting, but for a real application is a real core part of our company and the way our software works. So what are these requirements? Why do we need to do this? Well, each loan buyer has requirements about what type of loans they'll buy and what limits. They may say, we only want regular installment loans, no low AOV, no experimental loans. And they also have a concentration. They only want a certain amount, total volume of these loans in their portfolio. And then, once they have those loans, they want us to report on them. They want us to tell us about how their portfolio is doing. What is the repayment information? What does the default rate look like? How is their investment doing? So obviously, these need to be very accurate. The status of the loan is changing, and that changes the report that we're generating. So we're going to regenerate this from scratch. We're not going to do anything incremental. We're going to recompute this every single time. And what that means is you're doing full scans on these internal data stores in order to create these table interfaces, these reports that you can report on and maintain accuracy. So initially what we were doing is you have your data stores, and you spin up some batch jobs that scan that entire table, join the columns together, or do the join on the tables, but it still ends up being a full scan, create that report and send it off to the merchant or whatever. This is problematic for a lot of reasons. First of all, doing full scans on online databases, you've got to have read replicas for that. And as the number of your data grows, you got to scale up higher read replicas for that. And furthermore, it actually just doesn't perform very well. These jobs were running very, very slowly. So with our DB snapshots, we can actually improve this quite a bit. So we've already talked about how we take our DB snapshots and land them in the data lake. So now we can have a pipeline where this first set of jobs you see are essentially they're an ETL that's creating a table, and we think of it as an offline interface from these internal data stores. These are owned by the teams that know about this stuff, and exposing a file-based interface into our data lake for the Rody example, what is the loan grading, loan labeling, and that's used for eligibility requirements. In the settlement detail, consolidated view that abstracts all the complexity of what is the nature of the servicing loan, Is auto-pay enabled? Is there an APR rate? What is the repayment history? That has a lot of really interesting edge cases that this handles. And then those interfaces, these are now essentially tables in our data lake, can be used for loan buyer reporting, which is going to grab those things and create a report for a certain buyer for what the fields that they want, or loan sale eligibility selection, which is going to say, this is what we're about to sell. And a really key thing that I want to stress here is all of these components are actually two-way interactions. Your obviously end goal here is to send out a report to a loan buyer or to create a set of loans for selection that then someone in finance can approve and say this is what we're going to sell. But these intermediate things, the RODI, the settlement ETL, and even the reports themselves, have a lot of value. You can connect those to other data sources. You can query them to do analysis in your day-to-day running of the business. And so we get that essentially here for free with this design. We're putting everything we extract back into the data lake, and then we find, sometimes even unplanned to us initially, that these sources become very heavily used and very useful for analytics. So it's a huge value of the system. And of course, we're going to go ahead and put these in Parquet. These are actually already all written in Parquet by Spark, so we can really easily register them. Athena, Glue Catalog. So we already have an integrated way. We don't have to do additional work to make this stuff discoverable. It's already in our data lake, and we're going through a standard process that you've seen many times in my slides here to be able to query this data. So I'll talk briefly about machine learning. Machine learning is obviously a very data-hungry process. You need a lot of data and a lot of various sources, especially when you're doing experimentation and analysis, because you're trying to figure out what's new that's not already there that may add value to your predictions. So you really need the data lake to be accessible there. You also need it for model training. You need to feed data in order to train your model. And then you're going to use it in prediction decisioning, and you're going to generate new data in model prediction decisioning. And I'm not going to talk about all the ways in which machine learning utilizes our data lake, but I'll talk about a single piece of data that is really central, which is the fat log. And what the fat log does for us is it captures, for every checkout, what input data did we have at the time, what was our decision, and what was the result of that. And we're going to log that on every single checkout, and we're going to persist that to our data lake and use that as an input. So you end up with a pipeline that, again, it looks a lot like some of our other pipelines that we've seen. We're treating this essentially as a type of log. We're going to ETL it into Parquet, because these actually you really want in Parquet, because these have many, many columns, one column for every single data source that the decider saw, columns for different signal types. It's a very, very wide thing. So we put it in Parquet. You can select out the signals that you're looking for when you're doing this analysis. And we also do a quick ETL into Apache HBase. This is for debugging use cases. HBase is really good at looking up a single row in a vast array of data. And so if you're trying to find out what happened for a single decider run, a lot of our developers will use this for that. So what's going on here is that in decisioning, we're putting the data back in the data lake, and then we're using that data for new model training. And actually what we found is this data actually ends up being valuable for loan grading and loan sale selection as well. So again, we're putting it in a central place, and we can kind of pull from it when new scenarios arise. This was not built for loan grading, but it works for it. Okay, so I've talked about some use cases of how we're loading data into our data lake and why that's been valuable for us. I'd like to dive into how we're actually running these jobs, because that's an important component. In a lot of these diagrams that you've seen, I mentioned ETLs that we're running, batch jobs, various processing that we're doing. How do you run those things? So we obviously require batch jobs. We use Spark almost across the board here, because it's just a very easy interface for doing these transforms. It abstracts the file layer away. You just do a write, it'll do the format for you. It's really easy to scale up. In fact, we just had a Black Friday, Cyber Monday. One of our jobs started failing because it just didn't have enough capacity. We just tweaked the capacity, went up higher, no problem, job ran fine. There's a lot of architectural overlap in these jobs, and so it needs a shared framework. So what we have is something we call the Datatools framework, and we'll handle deployment, CI/CD, monitoring and alerting, scheduling, and cluster management and execution. And really this is all built around having the easiest way to operate and use Amazon EMR. Because that's the bread and butter here, right? EMR is what's going to run our Spark jobs for us. So what we've got here is base classes for heavy shared functionality. These are all simplifying the process of writing new ETLs. It's going to, behind the scenes, handle provisioning the EMR cluster, deploying the code, monitoring it. You don't have to write any code to do that. Common libraries for tasks. We're registering partitions into Spectrum all the time, so we're just going to hook that in as part of the library. We're copying from various formats, and we're loading from specific formats in a lot of different ETLs. We're pulling that data. So we're just going to provide some tools to do that. And then we're going to support, scheduling and deploying tasks. And so I want to talk a little bit about how we use EMR with MRJob, because MRJob is a tool that makes it really easy for us to use ephemeral clusters on EMR and to scale them up and tear them down while still not overusing the clusters and paying too much. So what MRJob does is you basically write your Spark code, and then you write some configuration that says, what do I want this cluster to look like? How many nodes? What is my Spark config? Stuff like that. And it's going to copy all of that up into S3. And then it's going to do some EMR API calls, and it's going to figure out which clusters are available for me to run this job on. In other words, which clusters are big enough for this job to run on, and are they available? Are they not running other jobs that are taking up that capacity? And if it doesn't find one, it'll spin up a new one. And if it does, it'll reuse the existing one. And then it'll tell EMR via the Steps API to copy the code that you've uploaded to S3 down and run our application. And then on your local process, it's going to pull on the step status and succeed or fail or clean up. And then it'll exit. And in particular, what's really valuable here is this concept of cluster pooling, where MRJob takes a hash of the cluster configuration you declared in a config file, and it looks for a MRJob pool hash value. And if it finds any cluster that matches that hash, it checks if anything's running on it. If nothing's running on it, you can schedule there. If something is running on it, you have some knobs that you can tweak, right? Let's say this job needs to run right away, it's very critical, you don't have any time to wait. You can spend the money, spin up some new capacity, and run that job there right away. But in other cases, you don't really want to do that, right? This job can maybe wait 10, 15 minutes, however. So you're going to tell it to wait, to poll for 15 minutes before spinning up a new cluster, still within your SLA, but you're going to save some money. And you're also going to save something else, which is that spinning up a new cluster takes about 5 minutes. You're going to make your jobs a little faster. And the last thing is, after these clusters are all done running, let's say you ran a whole bunch of jobs, and now these clusters are sitting idle, it's going to go ahead and automatically tear those down for you after a certain time of idle, so that you're not spending money on that. And this is the config that MRJob provides. You can configure your region, you can configure your cluster pooling, your Spark settings, and any kind of bootstrap that you have going on. So this is a really nice open source tool for us, and we really like using it, and it really helps us with our usage of EMR, really simplifies that. And it means that now in this framework, when we write jobs, we really just focus on the Spark code. So this is an example of dumping a Dynamo table. You just need to write your Spark. All of that other stuff is going to happen with this shared framework. Okay. So I've talked about the unified data lake, and we have all of this data coming into it, and we're using it for reporting, machine learning, analytics, and we're bringing that data back in. So now behind the scenes, that looks like all of this. So we're using database replication to fuel, we're using Lambda, and we're using DMS, we're using Kinesis to fuel our database replication, EMR to execute our jobs, Athena and the Glue catalog as this very central registry and discoverability tool, Redshift for our highly schematized and performance-sensitive work, and this is kind of, when you zoom out, everything that you have going on. So I would be lying if I said that this system's perfect. There's a lot of challenges we faced along the way and a lot of improvements that are yet to be made to meet this goal of a truly unified, discoverable, organized data lake. I'd like to talk about some of them. A few of the challenges we faced, I mentioned this before, but partitioning in Athena is not straightforward. You've got to think about what your access patterns are. Like I said, if you partition on a field that has a lot of cardinality, it's great if that field is always queried on, but the moment someone wants to not query on it, or query too many of them, you've got an S3 small files problem. Your performance is really going to suffer. The other thing is, Athena has a sweet spot of file size in which it performs best, right? If your files are too small, you're spending a lot of time downloading them, all the files over the network. If your files are too large, similar thing, you're pulling one file back down, you can't parallelize it as much. So there's a sweet spot, and you kind of have to experiment, and we experimented and found what that file size was. But even when you find what that file size is, Spark doesn't give you an easy way to say, my files just need to be 64 megabytes or whatever. Spark thinks about data in terms of partitions, and while you can adjust partitions and the size of partitions, if you make your partitions too large, it impacts your memory, it's not as scalable, and there's nothing really out of the box where you can say something like that, so we had to write some additional tooling inside of Spark to allow us to make that declaration. The other thing is MRJob. MRJob does a lot of EMR control plane operations. It lists clusters, it pulls on the status of cluster steps to see if they're running or not. When you start running too many tasks, each task has to do this, and you're going to start facing throttling. Now, not so much of a problem. Exponential backoff solves this problem quite well, but you do end up backing off quite a bit, and it delays the start time of your jobs. So we'd like to add a caching layer in there to reduce the redundant operations and bring down that rate so that we don't have to face this issue anymore. And a few of the things we think we can get better at as we work towards this vision is one, heavier utilization of the Glue catalog, and specifically the Hive Metastore integration that the Glue catalog has in our ETLs, and higher usage of Spark SQL. If you look through and think about the pipelines that I've mentioned, we're using Glue quite a bit, the catalog, to register the results of our ETLs and so on and so forth, but we're not necessarily using the Hive Metastore integration in our ETLs. We're relying a lot more on these API interfaces that I've described. And I think relying more heavily on the Hive Metastore, it just kind of brings everything back into that single way to discover and use this data. So we'd really like to get better at that. And that'll simplify the process of writing new ETLs, because you can really rely on the Hive Metastore and the Glue catalog for your discoverability. Likewise, Glue has this amazing feature where you just turn it on and it'll scan your raw data and discover the formats of your data and just register that up into the Glue catalog. That will just give us a lot more discoverability as well and continue to enrich the lake that we have. And I mentioned this earlier, lake formation has a lot of, they're calling it data ops now, tooling. We could probably simplify some of our operations and replication ETLs by looking more closely at lake formation. And finally, we'd like to have a more expressive system for data validation. Right now, every single job does its own validation tooling within their Spark code. But if you think about it, every single job does data validation. So we'd like to create a definition where when you're writing an ETL, you just define how to validate a row, and you define what to do if that validation fails. Do you accept the entire job? Do you put it to a dead letter? Do you, error out? Do you emit a metric? And then we can just consistently have every single job do that a certain way. So we just have more of a framework around how you do data validation, how you handle errors in that. Cool, so that is my talk. Thank you guys so much for being here, and thank you for listening. And do be sure to complete the survey in the mobile app. And yeah, I'm happy to take any questions if there are any.